So the last time in class, we had built this model up. This model, again, consists of stocks and flows. The stocks represent accumulations. The flows represent, and the stocks, therefore, keep track of the state of the system. Specifically, they record the number of people, say, who are susceptible at a given time, the number of people who are infectious, the number of people that are recovered. What do the flows represent here? So this flow associated with recoveries, for example, what does that represent? Yeah, it is. It is. It contributes collectively. The net flow into a stock indicates the rate at which it's changing. If there's bigger net flow in, if it's very, very large, it may be rising quickly. If there's zero net flow in, what is that stock doing? Zero net flow. It's staying constant. It's not changing over time. If there's negative net flow, in other words, if there's more flow out than flow in, so if waning of immunity, the number of people per week leaving by waning of immunity exceeds the number of people who are recovering per week, what is this stock of recovery going to be doing? If the outflow exceeds the inflow, think about your tub at home. You have the drain, water going out the drain faster than it's coming in. What is the water in that tub going to be doing? Decreasing. That's right. It's going to be falling over time. So the values of these stocks, ladies and gentlemen, as a reminder, are driven over time by the flows that enter or leave them, and specifically by the net flow. By net flow, I mean the sum of all flows in minus the sum of all flows out. And we saw last time that we could explain much of the behavior in terms of that. So we could understand, for example, the number of people here that are marked in this infectious state over time as a function of sort of the number of people getting infected on the one hand and the number of people recovering. And you may remember that we ran this out and the number of people infectious rose and then declined. And we could reason about why that is in a stock and flow level. Everyone started in the susceptible state, and therefore initially for the infectious state, what was going on? Why was it going up over time initially? The number of people in the infectious state. Why was it rising over time? Because the what? If it's rising, what must be the case? The inflow is greater than the outflow. And why is the inflow greater than the outflow at the initial time? Remember, everyone's initially starting susceptible. No one is starting infectious. No one's starting recovered. So why is infectious going up then? Yeah, lots of susceptible people getting infected. And how many people are getting recovered just at the start? None. There's nobody to recover. So rate of infections is greater than rate of recoveries. Maybe 100 people per week are getting infected, 0 getting recovered. So infectious shoots up initially. Why does it plateau? Under what conditions does it plateau? Why would a stock plateau?
All the flows are equal?
Yeah, the flows into and out of that stock are equal. The net flow is what? 0. And as a result, the stock isn't going up or down. It's like you have 2 liters a minute coming into your tub, 2 liters a minute going out. The water is staying at the same level. Okay, and then it starts to fall. Under what conditions will that stock fall? The stock of infectious. Why is this falling? It will fall if the greater than the inflow. And why would that be? Why would it be that early on the outflow was very small? That very on the stock was rising and the outflow was very small, and the the inflow is greater than the outflow, but now actually the outflow is greater than the inflow. Hence, the stock of infectious is declining. Why would that be? Give me a reason why. Why is it that the inflow for these time periods, for like time 50 and beyond, why is it that the inflow is less than the outflow here? Give me.
Smaller sample size to recover quickly.
Well, okay. So there's a lot of people who are infectious who are starting to recover. So the outflow is pretty big. After all, it reached this peak, right? It reached this peak, and so there's lots of people recovering now. And how about the inflow? What is that doing over time? Number of people per week who are getting infected, who are undergoing infections, what is that doing over time? Is it going up? Is it going down? It's most emphatically going down. Why is it going down? Well, the number of people who are susceptible is going down. Declining. Why is the number of people susceptible declining? Because there's very few who have already been recovered, and therefore there are very few people coming in with waning of immunity. And there's quite a few people who have gotten infected, and therefore it's being drawn down. That's the purple line here, right? Ladies and gentlemen, remember, these models are thinking tools. They let us pose some theory about what's going on in the world. That theory may or may not be correct. The models don't immediately tell us what is going on in the world, but they help us take a theory that's just sitting on our heads and uncertain, put it out in a place where people can look at it, critique it, help us refine it, but also critically where the computer can tell us the implications of that theory in terms of things we have difficulty calculating in our head. We have difficulty as people putting this all together and understanding what the implications are of this theory. By putting it here, we can see what the consequences are logically of these theories for things that are hard for us to calculate in our head, like the number of people susceptible, infectious, and recovered over time. And we can spot inconsistencies, say, with what evidence from the world suggests. In short, the models don't immediately tell us what is going on in the world, but they can help us more quickly identify inconsistencies between what we think may be going on in the world and what actually is, by allowing us to spot inconsistencies between the implications of that model and what we observe. We're not very good as people at calculating all these things in our head. Computer is much better at it through simulation. And we can see the results of the simulation for these quantities here, number of susceptible, infectious, and recovered. And we can see how that jives with what we know from the world through empirical evidence. So these models are thinking tools. Now, today, we're going to be expanding on this knowledge, and we're going to be talking about things that sit in three places in this model. To wit, this place here, and the number of infections, the number of recoveries, and the number of people who are over the rate of people who are getting infected, who are recovering, and who are waning in immunity. These three places here, these three locations, and these are called first-order delays. And first-order delays turn out to be key building blocks just above the level of stocks and flows. So we're going to be thinking about how they work, and a key element of them is that they're regulatory in character. So you folks may remember, this is key. I want you to really absorb this stuff. These are examinable things. So I'm running this thing out, and let's suppose I stopped it, and I were to perturb it. I were to affect this. And I asked you to do a little assignment at home to see not only how it would affect the value of these stocks, but how it would affect the fraction of people, say, who are infected, fraction susceptible and fraction recovered. We're going to do this. I mean, we could go and do this now just with respect to the stocks. We could suddenly increase the number of people who are infectious to 100. And what do you think is going to happen? Suppose I run this forward. What's going to happen? Okay, so what's going to happen with the number infectious? I just increased it to 100. So what's going to happen here? It's going to jump. And then what's going to happen after that? Is it going to stay jumped? Stay jumped. Is it going to stay high? Is it going to remain elevated? Okay, it's going to exhibit goal-seeking behavior. It's going to exhibit regulatory behavior. It's going to do what? Is it going to go up or go down? Down. Down is right. And to whence will it go? So I'm going to do this just about time 700, and I'm going to watch the results. It's going down just about to the level it had. We've actually increased the population size as a result of doing it, so it's slightly higher now. But it goes down to almost the same level that it had originally. And so there's kind of this goal-seeking behavior. I could perturb it in a giant way, 1,000, and we could see it jumps up and then it decays. Okay. So here we see that we can disturb the system, but it has a tendency to pull it back to a certain state. That's a regulatory tendency, folks. It's a tendency to kind of restore balance to the system. What sort of balance is exhibited here? Ladies and gentlemen, riddle me this. What sort of balance is shown here, where these are all, why are these lines all straight? What does that tell us about what's going on? It's steady state. And for each of these stocks, what does that mean? That stock is remaining constant, essentially constant. It's changed tiny, tiny, tiny bit, but it's essentially in balance. What does that mean about the inflows and outflows for that stock? The net flow is 0, and that's for each and every stock. In other words, the inflows, some of the inflows equal to some of the outflows. For each stock, the system is a kind of stasis, a kind of equilibrium. Now, when I asked you to do this as an assignment at home, I asked you to elaborate and compute for this model, not just the prevalence of infection, but the fraction of the population that's susceptible and the fraction that is recovered. How would I do that? I'm about to go do it, and you will guide me even as I move my mouse. Where do I need to go? Build those 64-pound weakling muscles. Help guide me. Where do I need to go? I want to go and compute over time the fraction of the population that's recovered. How do I do it? Okay, good. System dynamics. Just like that. Okay, here we go. And what do I add in? Dynamic variable. Indeed. Okay, good. And I'm going to say fraction recovered. Okay? Okay? What else do I need to do? So, on what does this depend? Speak, youths. On what does that depend? Good. Okay, good. So what do I need to do to show that transparently? Remember, when we have a variable, we like to transparently show on what it depends. And we have a diagrammatic notation that supports that stands before you. So what do I need to do to show that it depends on those two things? Add a link, yeah. And the link lets us, ladies and gentlemen, what you see, how many people in here have taken 340? Raise your hands as if in a phalanx. Okay, okay, that's a kind of weak phalanx. Is that all? Okay, most of you folks are many of you folks third year? Is that it? Okay, so you haven't taken it yet. You haven't yet seen the beauty, the majesty, perhaps the glory of functional languages. But what we're seeing here is a visual language. The language is actually computationally universal. Anything you can do in a Turing machine, you could actually do with this. Now, it wouldn't necessarily be pleasant, but perhaps you don't feel that Turing machines are pleasant. But it is possible. This is a visual programming language, actually. And by glancing at the model, we can see, even if we we hide some of the details, like the formulas. We can see what depends on what. For example, Waning's immunity here, we know it depends on this parameter and this number recovered. So if we have fraction recovered, we know it's going to depend on recovered, and we know it's going to depend on the total population. And so we hitch it up. And that tells us a lot. For someone who comes to this model and wants to glance at it and understand how it works, it's really helpful to have these links. They don't give you all the information, but they give you a lot of it. Okay, so option space is your friend, right? What's the formula here? Speak, as in one voice.
Number recovered over.
Good. Number recovered. Okay. So recovered divided by total population, right? And I suspect, you see there's this little X here. And that X is an indication that it's encountering build problems. So we can go to the problems window and, we'll see this is actually problems on another model. So I'm going to close this model without further ado. And now we'll go back to this one. Okay, so we just added this fraction recovered. And I'm going to do a similar thing very quickly for fraction susceptible. Okay, so I'm going to go here. I'm going to drag in this. I'm going to do fraction susceptible. And I am going to drag in a link and connect it up. And similarly, I'm going to drag in a link to total population and connect that up to it. And what's the formula for fraction susceptible going to be? You should be able to make a Greek course. Okay, good. So it's susceptible divided by total population, right? Okay, total pop. Okay, great. Build early, build often. Here's this build button up here. That will keep you in straight and narrow. It'll alert you to any problem quickly. Now, those who have taken 371 especially should be familiar with this notion. Why would you build early, build often? Why do you want to build very frequently? Yeah, exactly. Find an error early. Look, if you make a mistake, it's easier to sort of figure out where it is if all you've changed is a few things. So every time you reach the end of a kind of very small logical chunk of work, press the build button and see if it's happy. It'll say build completed successfully. If it's unhappy, it'll give you some errors, but there'll be a lot clearer and a lot fewer of them because you've done it frequently. So you'll be able to much more quickly find what went wrong because you've only changed a few things. If you only do that occasionally, if you only do it once every half hour, once you've built the whole model up, you may see lots of errors and you'll be lost. Where do I start? The errors will interact with each other. It got confused by one and then it doesn't understand the other. It's much better to build early, build often. It's the principle very similar to continuous integration, as we talk about in 371. Okay? Okay, so we're going to run this model now. And what I'd like you to look at here, mark my words, is let's go over to look at fraction recovered. And we're going to see that that rises and it continues to rise there. Here's the prevalence of infection, and that's rising. And you'll notice that these are rising and then changing over time for quite a while. They're in a sort of disequilibrium mode, but then they go down and essentially reach equilibria. Now, this is awkward. You folks are going to tell me, because you need these skills for the first problem set as well as elsewhere, how do I go add a way of viewing those things over time? Because it's going to add insight to what we do in the next little bit. How do I go view this in a plot? What do I do? Trying to get you familiar with this so it's easy for you to undertake common tasks. Okay, so go to the palette, go down to analysis, and we can drag in a time plot. I'm going to put it over here on the left-hand side. There we go, drag in a time plot. And what things in this time plot do we need to frob? So we're going to call it fraction in states time plot, something like that. And what do I need to frob? What do I need to do in these properties here? Tell me one thing for sure. Add data, that's right. So I need to I'm going to add data items for three things. To wit, fraction susceptible, fraction infectious, fraction recovered. Okay, fraction susceptible, yeah. And this is just a title. We can put anything there. It's just a string. It's nothing fancy. But the value of it will be given by what? Indeed. Okay, so now let's go at another one. This will be fraction that are infective, right, or infectious, as you see fit. Fraction in, no, that's not what I want. Oh, it's called prevalence. That's right. We call it prevalence of infection. And then finally, there should be one called fraction recovered. Okay, fraction recovered. And this, ladies and gentlemen, is just fraction recovered. Okay, let me go put those up there so that you can see them. So, fraction susceptible, fraction infective, and fraction recovered. Okay, this is exhibiting truculence. Okay, there we go. Okay, so we added those three things. Are we done? Are we done? Have we completed our frobbing? Good. Excellent, excellent. Things are sinking in. That's great. The point of this class is not to learn this, but to learn this particular tool set. But the tool set will be really helpful for you in exploring the problem sets, the conceptual challenges, the projects. So I do want you to have some familiarity with it. And if we scroll down here after these things, we will find that we want to display up to 1,000 latest samples in a time window of 1,000 time units. Okay? One keeps track of the number of data points that are going to be displayed at a given time. The other is the time window over which those are displayed. Okay, great. Okay, so let's, ladies and gentlemen, let us go and run this model. Who wants me to take a bit more time? Leave this up for a bit. A little bit? Anyone? Okay, let's compute. Okay, so let's go runner. I should have done a build first just to see. Okay, so I am now running this. I could have made it a bit larger. You'll notice that we're rising. Here we have rise, and this right now mirrors this one to the right. But now, ladies and gentlemen, there's going to be something different between them. I'm going to pause this, and I'm going to go change the number infectious to be 1,000. Okay, 1,000 here. What do you think will happen in both these graphs initially? We've added 1,000 infectious people to the population. Oh. Actually, in truth to be told, right now they're not truly infectious. They're not spreading it to others, but they're sick. Okay, so what do you think will happen in both graphs initially? Bo said it earlier. What do you think will happen? Speak. Well, we're going to see a spike in the number that are infectious. We're going to see a decline in the number that are a decline in the number that are susceptible. And then what's happening, ladies and gentlemen? It's coming back, and it's coming back to the same basic values, ladies and gentlemen, in terms of the fraction. It's a bit different over here. You notice over here to the right, this value after the change is actually elevated above it to the left. But over here on the left, it's the same. It comes back to the same basic equilibrium point in terms of the fraction of the population. This value here is higher in large part because there's more people in the population to the right. And so the counts, the actual numbers are going to be a bit different. But the fractions are actually the same. The fractions are actually dictated instead by these parameters, okay? These parameters here. And we'll see why that is when we, later in the semester. We could add 1,000 more people here, and once again, we will see it get perturbed and come back to the same state of balance. Same state in terms of the fraction that lie in each category. We could perturb any other stock as well. We could go alter the number of people who are recovered. We could grow the number of people who are recovered by 10,000 right now, okay? And we can go run this system. And because of the simple linear nature of the system, it comes back to the same equilibrium every time. We could add, what do you think would happen if I added 100,000 people? After all, the total population right now is 1,800 people. Suppose I were to add 100,000 people to the infectious stock. What do you think would happen? Same thing. It's just going to return to the same fractions, return to the same basic state. You'll notice it involved a giant spike up here. Almost everyone went into this state, but now it's declining. It's declining. Why is that? Why is it coming back so persistently to the same state? Well, there are several levels at which we could answer that question. But it's the nature of the system that it's regulatory in process. We have these several negative feedbacks associated with infections here, or with what's called infections, people getting sick, number of people getting recovered, and the rate at which people are waning in terms of their immunity. This is a little bit misleading to call this infections because we're actually not having the spread yet. That will be a positive feedback later. But right now we just have 3 negative feedbacks, and it leads to types of systems that tend naturally to homeostasis or to a state of balance. So let's go and explore a key mechanism in the form of forced order delays that explains that. Any questions about this before we go on to explain these building blocks that lead to this sort of regulatory behavior? Anything? Okay, yes.
I'm curious why, like when you initially run it.
Mm-hmm. Yep.
Let me just do that again.
Sure.
Why the peak on infectious doesn't occur at the same time as the intersection between recovered and susceptible?
Yeah, great question. Wonderful question. Remind me your name? Wade. So Wade was wondering, why is it that we get this cross between, you could look at it either in terms of the absolute numbers here or the fractions, between the fraction susceptible coming down here in purple and the rise here of the fraction recovered. And they cross at this point about 50%, about time 100, right? But the maximum number who are infective is actually occurring much earlier, maybe time, 10 or 20, something like that, time 20 versus time 100. Why is it that those are not occurring at the same time? After all, wouldn't you think that the net flow into infectious might be highest at this point? Well, let's think about that. So what determines this peak here? What determines this peak in the number that are infective? We said it earlier. At that peak, what is the case? Okay, yeah, or to put a bit of sharpness to that, the rate of infections, people per week, is the same as the rate of recoveries. I mean, another way you could phrase this is the number per week, yes. Not so much number, because number sounds like it's independent of time. It actually depends a lot on whether we measure things in weeks or months or years or days or milliseconds. it'll be different numbers. So we talk about the rate, the number per unit time. Okay, so at that peak, the number of infections per week is the same as the number of recoveries per week, or same thing per day, right? Okay, so at that point where these are in balance. Now, there's a question, okay, why isn't that when these two cross then? Because after all, the stocks are equal here, right? The values of the stocks, the values of the number susceptible and the number infectious are equal at this point around just short of time 100 here, right? That's when those are equal. Okay. So the values in the stocks are equal. Shouldn't that mean the number of infections are equal? Well, let's go, or the number of infections per week equals the number of recoveries per week. Let's go in and check that out. The number here of infections per week is given by this formula. Number is susceptible for sure, but times this force of infection. But meanwhile, the number of recoveries per week is given by infectious divided by recovery time. So even if infectious and susceptible have exactly the same values, the value of these flows might be different. Because after all, if susceptible has a certain value, what sets the value of this flow is not just the value of the number of susceptible, but also takes into account this number here. So in short, it isn't always the case that if you had number of susceptible equals the number of infectious, that these flows, the rate of infections, the rate of recoveries will be equal, because it also depends on these parameters. Is that helpful, Wade?
Yes.
Okay. Okay, great question. Other questions? These are fantastic. I love questions. Other questions? 3, 2, 1. Okay, sold. Okay, we're going to be going now to look at the building blocks that are leading to regulatory behavior there. So, to explore this, I'd actually like you to, we could do it with this model, but I'd actually like you, for simplicity, to build up a new model, okay? You can keep this one around if you want to, but we're going to build up a new model, which is going to be involving different, some simpler mechanisms yet, some mechanisms that will be a little bit easier to understand. So, ladies and gentlemen, call up a new model and call it first order delays 1. And I'm going to call it, for me, CMPT 394 here at the end. Okay? Okay. So, ladies and gentlemen, I would like you to have a representation of a population where we have immigration in and deaths out. And there's going to be no births represented right now. So there's a population with immigration and death going on. What's the stock? What's the flow? What's the stock? The population. Yeah, the number of people in the population, right? That describes the state of the system right now. The number of people who are around. Okay, good. So we're going to drag in a stock, and it's going to be population. Okay, how about immigration? What does that sound like? Yeah, if we say Saskatoon is really high, it's really high levels of immigration. We had an immigration of 1,000. You'd say, well, over what time? Last year? Last month? What is that? So we know it has to be a flow. We know it's a flow. It's something per unit time. Okay. So we're going to call it immigration, right? Immigration. Great. And then we're going to have a representation of deaths. What is that going to be? It needs to be a what? A flow also, because it's something per unit time, right? So we're going to drag here. Okay, deaths. Great. Okay, so ladies and gentlemen, I would like to go and put in place a dynamic variable here that will be called immigration rate, okay? And we're going to put in place another actually a parameter that's going to be the mortality rate, okay? And one thing I forgot to do for this model, but would be very helpful, is to set the time unit. Where can we set the time unit? You may have already done it. I'm going to set the time unit to years. Where do I go to do that? Sorry? For the project as a whole. That's right. It's a property of the project. It's not a property of sub-pieces of the project, but of the project as a whole. Okay, so if I go up to the project, I can set this to be years. Okay? Great. Okay, now, ladies and gentlemen, I would like you to establish this so that the rate of immigration as measured by this flow is simply set by this immigration rate. I'm separating them a little bit because I think it may be a little bit more visual here. It's kind of a coin toss in my mind. So immigration here will just depend on immigration rate, okay? And it will just make it a little bit more clear when we frob this, where it's changing. Now, you're going to tell me the formula based on the reasoning we gave last time for deaths. So the idea here is, suppose we had a mortality rate of 10% per year. 10% of the population died per year. What would and suppose there were 1,000 people in the population who are at risk of death. What would the number of people be on average on a per year basis who die? Anyone? Yeah, 100. Where does that 100 come from? That's right. Yeah. So 10%, so that's 0.10 times 1,000, right? Each person in the population, each of those 1,000 people has a 10% chance of dying. So for each of them, they have this 0.1 probability of dying for the whole year. You want to total up the expected value of the number of people dying, is the number of people at risk times this mortality rate. Many of you will have seen that in your probability class. It's the expected value, right? Your expected value, if you have a flip of coins, each of them has a certain chance of, say, a 10% chance of turning heads. You flip 1,000 of them, you get on average 1,000. It's the expected value. So let's go hitch that up. So we want to hitch up death needs to depend on population. How do we know it needs to depend on population? I mean, we just gave a formula, which is great, but intuitively, how do we know it has to depend on population? I emphasized it last time. Suppose you were to see a model where it doesn't depend on population. Why might you be suspicious? Yeah, and if there's 0 people, I mean, it's an outflow from it. If there's 0 people in the population, how can anyone die? It's got to depend on it some. And similarly, if there's a lot more people, presumably there'd be more people per month dying. So it's got to depend on population. There ain't nobody to die if nobody's going to be dying. So so here we have to have deaths depend on population times mortality rate, right? We saw that earlier. Each person in the population has, say, a 10% chance of dying. Okay, so this is good. And I'd like to set, ladies and gentlemen, the mortality here to be, let's set it to a value of 0.02, okay? Okay. And we set the formula for this to be population times mortality rate. And for the immigration rate, ladies and gentlemen, I'd like to set it to be a value of 10. Okay, Value of 10. 10 people per year coming in. Great. And we're going to start the population with no people initially in it. So what is this population going to do over time? If we ran this, what will it do over time? Anyone? It will increase over time. Okay, good. And will it increase just linearly? Will it increase just rising at the same rate no matter how far we run it out?
No, it'll curve like this.
Okay, so it'll be rising initially faster and then curve like that. Why will it curve like that? Exercise that reasoning that we've seen in that more complicated example. Why will it rise up and plateau? Because as population rises, what will also rise? The rate of deaths, right? The larger the population, more people are going to be dying per month. And it will continue to rise until what point? At what point will it no longer rise? If what equals what? A stock will be in stasis, won't change if what equals what? Rate of inflow equals outflow. Yeah, rate of immigration equals the rate of death. And as population rises, what will be going up? The rate of deaths. Rate of immigration, as we've shown it here, it's just going to be a fixed thing so far. It's not going to depend on population. You can see there's no link from population to immigration rate. So population will be rising until the point where what equals what? Death equals immigration, in which case it will be flat. It will be rising up to that point slower and slower because the net flow will be going down even prior to that point. The net flow being immigration minus deaths. The bigger population becomes, the less of a gap there'll be between immigration and deaths, and therefore the rate of change, the net flow will be smaller, and therefore population will tend to rise more slowly. So let's run this just as a sanity check here. Let's run this. Okay. Oh, immigration rate, folks. We set it to 10. Yes, that's right. We did do that. Okay. Okay. So who needs Alan's help? He stands, a stalwart son in the back of the room. Okay, great. Okay, here we go, and we will see the population rising, and just as Wade spoke, we will see it rise, and then we'll see it plateau. Okay, Alan, sector 1, front. Okay. Okay, so it's rising, but it's rising slower over time. Initially, it almost looked linear, but now it's becoming smaller and smaller. Okay. Now, the rate is becoming smaller and smaller. The rate of rise, and if we run it far enough, we will see indeed it bends just as Wade predicted. It's going to be increasingly curvilinear, just like that. Okay. So, ladies and gentlemen, I want you to riddle me this. To what point is this headed? At what point will it be in equilibrium? At what point will immigration equal deaths? Okay. Okay, so we have formulas here, right? The immigration equals 10. At what point will immigration equal deaths? Okay, well, immigration is 10, right? And on the right-hand side, what do we have for deaths? This is immigration, the rate of immigration, 10 people per year. Okay, on the right-hand side, we have deaths, and deaths is given by what? Population times mortality rate, right? Mortality rate. So, please, folks, characterize for me at what population, and what is mortality rate here? It's 0.02, right? Right? At what point will this thing be true? At what population will we have this equality hold? Okay, so simple algebra, right? We're solving for population. Solve for population, we do what? Divide. Thank you. We divide 10 by 0.02, right? 10 divided by 0.02 equals population, and this value happens to be what? 500. Thank you. 0.02 is 1 over 50, right? And so we have 1 over 50 in the denominator. You flip it up, 500. 50 times some 10. So that's equal to 500. At 500, it will be in balance. In what sense? In the sense that immigration rate equals death rate. So it is kind of coming into balance. And we could destabilize it. We could double population, but again, it will come into balance in the same way. So we can, let's do that. Let's go see that. Okay, so we could go here and run this, and we will go watch population here, right? Oops. Go watch this, and we could run it forward until it's getting very close to its value, and then we could stop it. Say at time between 100 and 150, we could make it 10,000 population, and now we could run it out again. And what do you think it will be doing now? It will be declining. Why will it be declining now? I just made it 10,000. Why will it be declining? Give me the mechanics of it. What will be going on? This is 10,000. What will be going on? Outflow is going to be much greater than the inflow. And so it will be declining. To what value will it decline? 500. The same value we had earlier. Why? Because that is set by this parameter, mortality rate, and the rate of people's arrival and immigration. And we could go perturb the population, punch it, increase it, decrease it, and it will always be trying to restore to that value where the two are in balance. Right? If population is much larger than it should be, we will have a much larger number of deaths than immigration. It will draw down the population. The net flow will be negative. There'll be many rate of people going out is much greater than the rate coming in, so population will be drawn down. And therefore, it will tend to go lower and lower until the point where deaths equals immigration. Right? On the other hand, if population is too low, if you start with population 0, it will be rising very quickly initially and until the point, and then eventually number of, and deaths will be less than immigration, so there'll be a gap and it will be tending to fill up. It'll be a positive net inflow. Will tend to rise and rise, but as it rises, the death rate will increasingly come closer to the immigration rate until the point where they're in balance. Okay. So that's a simple mechanism. Do you appreciate that? Do you have an understanding? Do you have an intuition for that? Do you have an intuition why it's self-adjusting? Why it's regulatory? If it's out of whack, population is too high, it will be drawn down by its own mechanism, by its own mechanics. It will draw it down. The deaths will be greater than immigration. If population is too low, it'll be drawn up, because immigration will exceed deaths and therefore it will tend to rise. Make sense? I want you to be rock solid on this because we're going to be depending on this for a bunch of other examples. You feel comfortable with that? Okay, that's why it's being drawn back into balance. Okay, so now let us, ladies and gentlemen, go and explore further, okay? Great. So what we're going to do here is we're going to put in place an immigration rate that's no longer fixed. It will actually vary programmatically. We will set it. We won't frob it directly. We will go set a formula. So immigration rate. Now, all those daughters and sons of Java who have struggled through many courses with Java as the standard, you're going to tell me, I'm going to put in a formula here. I want to put in a formula which will give the immigration rate as a function of time. If time is less, and I'll tell you that time can be accessed by calling time begin paren end paren. So if time is less than time 50, I want the value to be 0. Otherwise, I want it to be 50. How would I do that? In an expression. This is an expression. This is a formula. It's not a statement. It's not an if statement. It's a formula. How would I do that in Java? With an expression. Okay, I'll give you a hint. If time is less than 50, then I want to be 0. How would I do that? Otherwise, 20. Anyone? Question mark. Good. 0, otherwise 20. Right? This is called the ternary operator, right? Ternary because it has 3 components. It's the condition to be checked. It is the value if it's true and the value if it's false. So let me phrase that again. It's time less than 50. If so, use 0. Otherwise, use 20. And I put the whole thing in parens. Make it a little bit clear. Okay? Are people comfortable with that? Ladies and gentlemen, build early, build often. Great. Okay, now, having done that, and still starting population at 0, I want you to tell me what's going to happen over time, do you think? What's going to happen to population over time? Then what's going to happen at 50? Okay, and why 1,000? Okay, so 1,000 comes from the fact that we are going to have an inflow here of 20, right? And at what value of population will the deaths be equal to 20? That's at what point population will be in balance, right? If deaths equals immigration. Immigration is 20. It's going to be 20. We're going to have 20 equals population times mortality rate. Mortality rate is 1 over 50. Bring it on the other side. You're going to have 20 times 50, or a value of 100 for population. At a value of 100, the death is going to equal, so a value of, 1,000 for population. At that point, deaths, the rate of deaths will be 1,000 times mortality rate, right? Times 0.02, which will be 20. Those two will be equal. Do you grok that? Grok or not? I gotta have fun sometimes. Okay, so are you comfortable with that, right? At a population of 1,000, what is the rate of deaths? Speak. It's going to be 20. Population 1,000 times mortality rate, which is 0.02, right? So it's going to be 20. At that, and 20 is going to equal the inflow, immigration, which we said is going to be 20 after time 50. So, indeed, remind me your name? Arlen. As Arlen said, this rose until a value of 1,000. So let's go run this thing. Let's go run it. Okay. And what we will see is here, you notice time is a ticking, and what's going on with this population? Anyone? Well, it's not doing anything. Why isn't it doing anything? Because it's not yet what? Time equals 50. Okay, now, boom. Okay, it starts rising. And just as Arlen said, as the sun follows the dawn, it's rising up, and it's rising up towards a value of what? Towards a value of 1,000, indeed, yeah. Towards towards a value of 1,000. So you could see here it's 930, 940, etc. It's rising up towards a value of 1,000. Good. So that's great. Now, I want you to tell me, though, how would that rise? So we have something like this. Rising up, it rose up something like this. Towards a value of 1,000. And this is, I should have drawn this carefully, this would be time 0, this is time 50, and it's rising up towards a value of 1,000 here. Forgive the artistry, or lack thereof. Something along those lines. Okay? Towards a value of 1,000. Okay, now suppose I were to change the mortality rate. We're drawing here the stock. This is the stock, okay? The value of the stock. Okay, up towards 1,000. Well, even before thinking about changing the mortality rate, if I were to draw out the graph instead for the outflow, for deaths, what would that look like? Here's time 50. Here's time 0. And suppose this is the rate of death. So I spelled it with a lowercase, so I will try to retain that. Deaths, the rate of deaths. A number of people per year dying. What would that look like? What is it for all this period? 0. Why is it 0? Because there's nobody to die. There's no one in the population, right? The population is 0. Okay, how about after this? What will it look like? It will look like what? Okay, so will it look like this, linearly rising? What's the formula for deaths? What's the formula for deaths? I'll go put it up here so you can see it in all its glory. Okay, that's its formula. So how will it be rising? So will it be rising or falling? Rising. After all, it started at 0. You can't have negative deaths. Okay, good. So it's rising. Indeed. How will it rise? This is the formula there. How will it rise? Exponentially. Okay, so I love suggestions, and I really value these. That's great. So will it look like that? How about any other suggestion? Yeah. Good. Your name? Ben. So Ben's suggestion is, well, look, the value for deaths is just population times a constant, right? This mortality rate is just a constant, right? It's 0.02. So the value for deaths will be changing proportional to the population. It would just be like a mirror image of the population. So Ben's suggestion is that it will look something like this, just like a mirror image of this, just scaled, just changed with a scale. It's going to be, there's some mortality rate times that, so maybe mortality rate is 0.02, so it will be rising up to what value? To 20. Where did that 20 come from? Why 20? Immigration. That is the value at which what is true? Inflow equals outflow. So it's not rising to 20 by chance. It's not running to 20 just as a fluke. It's rising to 20 because at that rate, at that point, at that rate of deaths, what will be the case? The stock will be in balance, and therefore the population will stop rising, right? It's going up. The closer this guy, the rate of deaths comes to 20, the slower the stock will rise. Why? Because the net flow in, immigration minus deaths, will be smaller and smaller. It'll be less of a gap between them. Early on, with the population starting at 0, deaths is 0, There'll be a big gap between them. And therefore, population will be rising very quickly. Lots of people coming in, no one going out. But over time, deaths will be rising. And because death is rising, immigration minus death will be smaller, and therefore the population will rise slower. And because population is rising slower, the deaths will rise slower. So this guy here, Ben is right on the mark. This guy here will rise just like the population there. But will rise up to the value of the inflow. Thank you. Darn right. So rise up to the value of the inflow. It's exactly right. It's exactly right. Okay, now, how quickly will it rise to the value of the inflow? Well, it turns out that this depends, and watching the time, I want to move on to an additional topic within the scope. But how quickly it rises, that will depend on this mortality rate. The mortality rate is very, very small. It will reach equilibrium, but it will take longer or shorter time. If the mortality rate is very small, it will take longer to reach equilibrium. Why? Because it will take a longer time for the population to reach a level where death equals immigration. Take longer to reach that point. If the mortality rate is very high, it will tend to reach it sooner or later. Sooner. Why? Because it will take less time for population times that mortality rate to equal immigration. Okay, so I'm not going to show this to you with the depiction, but it looks something like this, ladies and gentlemen. And we could phrase it in terms of kind of delays, which is actually 1 over the mortality rate, or in terms of the mortality rate. But either one, deaths will be rising up to the value of the inflow, either sooner or over a longer period of time. If that mortality rate is a smaller value, it will take longer for it to reach equilibrium. Deaths equal immigration. If it's a higher value, it will reach it sooner. Okay. Meanwhile, if we were to change those death rates, the equilibrium size of this population is going to be very different, right? Because the equilibrium size of this population is going to be 10 divided by the mortality rate, right? 10 divided by the mortality rate here, or 20 divided by the mortality rate, whatever the rate of inflow is, the inflow divided by the mortality rate. So if the mortality rate is smaller, the equilibrium value of people will be larger. It will take more people to make this rate of outflow, rate of death, equal to immigration. Because mortality rate is smaller, we need a bigger population to reach a certain level of immigration rate to equal. Does that make sense? Grok or not? Grok. Okay. Okay, so we can think, ladies and gentlemen, of these inflows as kind of delayed versions of the outflows as delayed versions of the inflow. If we have a very small mortality rate, for example, we'll get a long delay, as it were, before the outflow equals the value of the inflow. On the other hand, if it's a very high mortality rate, it will very quickly adjust. And we can see this as kind of a little bit like a delayed version of the input. The output, the deaths, will rise to the value of the inflow, rise to the input, just with some delay and with a curvilinear character, just like this. And you can experiment with it, and you will see different delays. Okay, what if the stock doesn't start empty? Well, if it doesn't start empty, it will kind of try to come into balance while the inflow is 0. It will decline towards zero, and then when that immigration rate suddenly bumps up to 20, the stock will start moving towards its equilibrium value. Okay, we'll get this kind of. In each case, it's seeking some balance. Here, it's seeking balance with zero inflow, and now it's seeking balance with this 20 inflow. So it's associated with goal seeking here. It is seeking this goal of having inflow equal outflow, seeking this goal of having death equals immigration in this particular case. And you can perturb it, you can inject changes to the system, that it will try to recover to this point where inflow equal outflow, where death equals immigration in this case. And again, if the stock is too big, population is too big, deaths will be much higher and therefore it will be drawn down. If it's too small, deaths will be smaller than immigration, so it will be drawn up. Okay? And it's going to be trying to reach this point where inflow equals outflow, in this case of a first-order delay. So, in short, we have this kind of rate of inflow, and we have some rate of outflow, and subtracting the rate of outflow from the rate of inflow yields some sort of surplus. There's some gap between the inflow and the outflow, right? And that gap tends to increase the stock, which in turn increases the rate of outflow. You got that? Right? So here we have this stock. We have inflow. We have outflow here. The outflow. There's some net inflow, which is inflow minus outflow. Right? And the bigger that net is, the bigger the stock will become, and therefore the higher rate of outflow. And therefore the smaller this gap will be. So it tends towards a situation where the rate of outflow equals the rate of inflow, where there's no surplus. If there is a surplus, the stock increases, and it tends to eliminate the surplus by increasing the outflow and therefore lowering the surplus. If it's a negative surplus, if the outflow is greater than the inflow, then the stock will be decreased, tends to lower the outflow, and therefore the surplus will also be eliminated, or the negative surplus, the deficit. So in either case, it tends towards a situation where inflow equals outflow. It is a self-balancing system. Do you folks appreciate that? Do you have some sense? Okay. This is foundational for interpreting some of our models in the next session. Now, I want you to pose to yourself now a question. We have this stock and flow model here. We have this stock and flow model. And what I'm telling you is that the dynamics of the stock and flow model depend purely on the net inflow. When I say net inflow, what do I mean? What do I mean for this particular case? Immigration minus deaths. Immigration minus deaths. So, I want to challenge you. Ladies and gentlemen, to go off and create for me a version of this model, which is going to have just one flow associated with it. And that flow will be an inflow. Okay? Now, I'm going to go create this in front of you to give you a very concrete sense of what I mean. And then I would like you to muse on it at home and to try to flesh out its pieces so that you can come back and answer me a question on it. So here we have population 2. I'm just going to be redrawing this in a different way. And this is going to be, ladies and gentlemen, this is going to be, here, immigration. This is going to be actually net. It's going to be net immigration. Okay. Oops, sorry. Its name is going to be net immigration, not its formula here. Okay. Its name will be net immigration. Okay. And I tell you that I want the dynamics of population 2 to be identical to population. So how would I do that in the closing 5 minutes here? How would I do that? How am I going to have this have a single flow in that has the equivalent situation to that? Well, remember, what I'm telling you is the population is only affected by the net, inflow minus outflow. So what do you think the formula for this will be? What must it depend on? Okay, it has to depend on the population. I love it. Thank you. So it has to depend on the population. After all, this one depends on the population. The dynamics of this depend on the population. The number of deaths per week depend on the population. Okay, what else must it depend on? What else does this depend on? Okay, immigration rate. I'm first going to concentrate on mortality rate here. Okay, because it depends on mortality rate, right? If we change the mortality, I told you, as we change the mortality, we will see dynamics change. As we change mortality, we will see this rise faster or slower. And so it has to be the case that this one will depend on mortality rate as well. Okay? Yeah. Great. So that much is the case also. And then it's got to depend on something like the immigration rate. Okay? Okay. So let's see if we can come up with a scheme for this. What must the formula be here for these two to be the same? Okay, remember what the formula was for above. If we have inflow here, the inflow minus outflow, the inflow is immigration rate, right? Immigration rate. Okay, good. Okay. And what is the outflow here? What's the formula for outflow? Population times mortality rate, right? Okay. So, ladies and gentlemen, this flow has to have the equivalent of these elements in it. Okay? Sorry? Right. Right. So if that's the case, we could actually put this in, and I will claim that it's an equivalent structure. Now, you may wonder why in the world I'm doing this. Well, it turns out that we'll be able to use it to very good effect. So we could just have this be given by immigration rate here. Okay, immigration rate. And then minus population 2 times mortality rate, right? We're trying to have population 2 have exactly the same dynamics as population here. So they have exactly the same dynamics, okay? And I would argue this bottom one has exactly the same dynamics, okay? Why? Because it's the net flow. It's the only thing that determines the value for population here. It's the net flow. So net immigration here, if we have immigration rate minus population 2 times mortality rate, we will get the equivalent of the net flow here. I would argue that they are going to exhibit the same behavior. So let's check this out. And then as your assignment here, I'm going to have you Okay, so initially they're both 0. Now we're going up towards time 50, and they're both changing. You notice at any one time, they're precisely the same. Precisely the same. So, I'm going to tell you one fact. When I introduced first-order delays, I noted that they could be phrased in one of two ways. As population times some rate, say, or as population, so I'll just make it a stock times some rate to make it more generic, a stock times some rate, or it could be phrased as a stock what? Divided by some delay. And the delay here is just 1 over rate. 1 over the rate, okay? These two things are mathematically identical. If delay is 1 over rate, stock times rate is the same as stock divided by delay. Okay. So, what I want you to do is to come up with a formulation where this inflow here is of the following form. It's going to be, so if I have a stock and I have an inflow and I have an outflow, if I have an outflow, what this will be, and I have some delay associated with this. This is the delay. What we will have instead in this sort of formulation is a stock, the same stock here, okay, where this inflow is given by, there's going to be a gap here, and the gap, well, okay, I'll just put it all in one formula. So it's going to be inflow, it's going to be a target minus X over some delay. And the question for you to ponder is, this is the same delay, this delay up there. The question for you is, what is this target? What is this target? We could phrase it as this. Here's a target towards which X tends, and the value of this flow will be target minus X divided by delay. Okay? And I want you to try to figure out, what is target? How does target depend on the value of inflow and the value of delay for these two to be equivalent? So, just as a reminder, this is X divided by delay here. And this is the inflow. This is the formula for the outflow is X divided by delay. You should be able to re-specify this in this sort of form using what we've just done here so that we could specify this formula as target, some target minus X divided by delay. And the question is, how does target depend as a function of inflow and of the delay? I want you to tell me what the formula for this is going to be in terms of those. So please go off and think about this, and we will finish covering this next time. Okay?